Welcome back. In the last video, we looked at separable differential equations. Now, if an equation is separable, meaning that we can separate the equation where on the one side we have the dependent variable and on the other side we have the independent variable, it can lead to a somewhat easier integration. Note that when we assumed a drag relationship where the drag is proportional to the square of the velocity, we no longer have a linear differential equation, and therefore the method of the integrating factor is no longer applicable. So let's have a look at what the solution looks like when the drag is proportional to the square of the velocity. So here's our skydiver, and we're going to do our free body diagram again. So again, the drag always opposes the motion, so the skydiver's falling, and so we have the drag which opposes the motion, and we have the weight. Okay, we should also assume a positive sign convention, so we're going to say that y is positive upwards. As always, it is Newton's second law that governs the motion. So let's write it out. We have the mass times the acceleration, which is equal to the sum of the forces. So as we can see, the drag force acts in the positive direction. So we're going to write the drag force. So again, proportional to the square of the velocity. So let's write kv squared, where k is some constant, minus the weight, mg. Now that constant, again, it can be proportional to, usually it's proportional to the surface area of the object that's falling through the medium. As well, you're going to have some dependence on the density of the medium, so in this case, the density of air. Okay, let's put this into a somewhat standard form by dividing by the mass. So we have the time rate of change of the velocity is equal to k over m v squared minus g. So it is not readily apparent that we can separate this equation. So we're going to have to do a few algebraic tricks to make that happen. And again, I warned you of this, that although it is nice if we can cast it neatly into a separable form, it often takes a bit of work to get it into a separable form. Okay, so what we're going to do is that we're going to define a new variable, or a new constant c, which is equal to the square root of mg over k. So what this leads to is dv by dt is equal to, so what we're going to do is factor out the gravity. So we have k over mg minus 1, and we have the v squared over here that I forgot. So that equals v squared over c squared, because we see we have that mg over k term, which is the inverse of c squared, minus 1. Again, this can be further simplified for our purposes as v squared minus c squared over c squared. Okay. So it is not in the final form that we can directly integrate, but we're getting close. So now what we're going to do is that we're going to separate the variables. So as we can see, we have this nice bracketed term over here where we only have, the only variable is the velocity. So we can put the velocity terms on one side of the equation. So we have c squared over v squared minus c squared dv by dt, and that will be equal to the gravitational acceleration. All right, so now multiplying both sides by dt allows us to set up our integration. So we have g dt. So on the right-hand side, our variable is t. On the left-hand side, our variable is v. We can integrate directly. All right. So now what you can do, you could definitely use some freely available software like Wolfram Alpha to look up this integral over here. You can also look up integral tables, but sometimes integral tables will not have an integral of the form that you are dealing with. So what we need to do, let's work out what this integral on the left-hand side is. So we can express the integrand. So let's just look at this over here. This 1 over v squared minus c squared can be expressed as 1 over v plus c and v minus c. And that's just a difference of squares. So when you have a difference of squares, you can factor it in this form. And this can be expressed as a partial fraction expansion. Now, if you don't remember what a partial fraction is, I would encourage you to go back in your notes and have a look at how to deal with partial fractions. All right, so setting everything up on a common denominator, so we have a v minus c plus b v plus c over v plus c and v minus c. And all of this is equal to 1 over v plus c, v minus c. So what we need to do now, looking at the numerator, we want to equate the constants and the variables. So what we have here, we have no terms on the left-hand side that involve the velocity, whereas on the right-hand side, we have an a term and a b term. Now, the constants on the left-hand side are 1, and on the right-hand side, we have minus ac plus bc. So this is a system of equations. 2 equations, 2 unknowns. Easily solvable, and we find that a is equal to 1 over 2c, and b is equal to 1 over 2c. Okay, so we go back, and we substitute this partial fraction expansion in here, which allows us to integrate much more easily. So we have c squared multiplied by the integral of a over v plus c. So a is minus 1 over 2c v plus c dv plus the integral of 1 over 2c v minus c dv. And this is equal to the right-hand side, which is the integral of g dt, which is just gt plus a constant of integration. Now that constant of integration, we're going to call it, we've already used k over here, we've already used c, so let's pick another letter. I'm going to pick z. Okay, so we can integrate this fairly readily. So this is minus 1 over 2c ln of v plus c plus ln plus 1 over 2c ln of v minus c. And that is equal to the right-hand side. So we see we have c here. That can go away. And now we see we have the difference of two lns. So we can simplify this as c over 2. So I'm just factoring out the 2, or the 1/2 rather. And we have ln of v minus c over v plus c. And that again is equal to gt plus z. So let's assume that the skydiver has no vertical velocity initially. So stated mathematically, v at times 0 is equal to 0. So if we substitute this initial condition into, let's call this equation 1, we find that z is equal to 0. So this reduces our solution to c over 2 ln of v minus c over v plus c is equal to gt. And what we can do is that we can actually just move these to the other side. So let's write this as 2gt over c. Now we're going to take the exponential of both sides, which will give us v minus c over v plus c, and that is equal to e to the power of 2gt over c. And remember, what we're looking for is v of t, so we want to try to isolate this somehow. So let's just take a few more steps, and I'll leave that to you to do this at home. What this results in is c multiplied by e to the negative 2gt over c plus 1 divided by e to the negative 2gt over c minus 1. This is our solution. So what have we just done? So knowing from first principles that the motion of the skydiver is governed by Newton's second law, and modeling the drag as kv squared, which is a fairly accurate assumption, we found an expression for the velocity of the diver at any point in time. So let's look at again when time goes to infinity. So for very large times, what happens? These two exponential terms, they go towards 0. So what we're left with is v at infinity is equal to c multiplied by minus 1, or minus c, which is equal to minus square root of mg over k. And that again is what we call the terminal velocity. Now notice that when the drag was equal to kv, that was when we looked at linear first-order equations, the terminal velocity, which we'll call v infinity, was equal to negative mg over k. Now, when f drag is equal to kv squared, v infinity is equal to negative of the square root of mg over k. And if you were to plug in typical numbers for the mass and the gravitational acceleration in k, what you would find is in fact that our second form of the equation is much more accurate and much more realistic. And again, the interesting thing in both cases is that both terminal velocities are independent of the initial condition. That's a very neat result. And again, notice that because of our sign convention, our terminal velocity is negative. And what that means is that if we have 0 over here, this will be negative c over here, and our falling body will approach this terminal velocity asymptotically. Where again, this is time, and this is velocity over here. So a very similar result, but our value for c is different compared to the linear case.